Cooling towers are a key part of many HVAC systems. They remove heat from water-cooled chillers and water source heat pumps and release it into the outside air. Cooling towers can be broadly categorized as dry or wet. In HVAC systems, we only use wet cooling towers since they rely on evaporation to achieve the lower water temperatures needed. Because of that, we won't cover dry types here. Cooled water from the cooling tower is pumped to the condenser of a chiller or water source heat pump where it absorbs heat. That warm water then returns to the cooling tower and flows over the fill material. Fans draw in outside air and a small portion of the water evaporates. This evaporation removes the heat and the cooled water is recirculated back to the chiller or heat pump. The performance of a cooling tower is often described by its approach temperature. This is the difference between the temperature of the water leaving the tower and the ambient wet bulb temperature. A small approach means the tower is more effective, but also usually larger and more expensive. Cooling towers come in several types. Open circuit induced draft towers are the most common, with fans at the top drawing air upward through falling water. Forced draft towers place the fans at the air inlet, pushing air across the fill. Closed circuit towers or fluid coolers keep processed water separate in a coil and circulate spray water and air around it. These are useful when water cleanness is critical. As mentioned earlier, there are also dry type cooling towers as well as hybrid dry-wet designs, but these are not commonly used in HVAC systems. Cooling tower capacity is measured in tons of rejected heat, which corresponds to the condenser heat load from the chiller or heat pumps. The heat rejected at the condenser Q of H is equal to the cooling load Q of C plus the work of the compressor or W. For example, a 500-ton water-cooled chiller requires a cooling tower that can reject not only the 500 ton of cooling load, but also the additional compressor work turned into heat. See an example of cooling tower capacity calculation in the notes. Cooling tower capacity and performance depend on the outdoor wet bulb temperature. In hot, humid climates, towers can't cool water as effectively because the air is already close to saturation. In dry climates, they perform very efficiently, but water use is higher due to increased evaporation. Cooling towers need careful placement. They are usually outdoors, often on rooftops or in service yards. Towers require large volumes of air, so they must be sited to avoid recirculating their own exhaust. They also create drift and noise, which can affect nearby buildings. Tower efficiency depends on fan energy, water distribution, and approach temperature. Even water distribution across the fill ensures maximum air-water contact, improving heat transfer and reducing wasted pump energy. Variable speed fans and optimized water distribution reduce energy use. Since towers are a major water and power consumer, efficiency improvements can yield significant operating savings. When selecting a cooling tower, engineers must consider the capacity needed for connected chillers or heat pumps, the local wet bulb climate, and seasonal variations, available space and a structural load on roofs or pads, noise limits and drift control requirements, water treatment needs since open towers can scale, corrode, and support biological growth, first cost but also life cycle cost, including energy, water use, and maintenance. This video is part of the HVAC Fundamentals course on AEC Learn. If you found this helpful and want to become an HVAC engineer, visit aeclearn.com. And don't forget to subscribe to the AEC Learn channel on YouTube.